our last example will be to calculate the work performed by a magnetic field. So here I have a current I that flows along the z-axis, okay, in the k direction. So imagine that I have the current here, and the strength of that current, we're going to say is going to be I. And what that does is that current flowing in that z direction induces a magnetic field. So it induces this magnetic field around it. And that magnetic field is going to be given by a constant c times I, and then divided by x squared plus y squared, and then times the vector negative y x. Now, I want you to notice that the curl of B in this case is going to be 0. So I'd like to find the work that's performed by this magnetic field around C1, and C1 is going to be a counterclockwise circle of radius A. So the first thing that I'm going to do for this first part of the problem is I'm just going to parameterize the circle. So here R of t is a circle of radius A, so it's going to be A cosine t, A sine t, and 0. And then R prime of t, well, that's going to be minus A sine t, A cosine t, and then 0. So to find the work performed, I'm going to need to do B dot R prime of t. Well, first I need to just figure out, well, what is B of R of t? Well, B of R of t is going to be Ci over x squared plus y squared, which in this case is just going to be a squared. And then it's going to be negative a sine t for negative y, and then x is a cosine t. Now we can look at B dot R prime of t. So that's going to be Ci over a squared, and then times, okay, so our B dot R prime is going to give me an a squared sine squared t plus a squared cosine squared t plus 0. Okay, we're thinking about B as having a third dimension, but that third dimension there is going to be 0. Okay. Well, what does that mean for the work performed by this magnetic field? Well, the work is going to be the integral of B dot dr. So that's the integral from 0 to 2 pi. Okay, well, sine squared plus cosine squared is 1. And in fact, this cancels with the a squareds as well. So in fact, this B dot r was just C times I. So we're going to integrate C times I dt. And so the work performed is just 2 pi Ci. Well, that was just a work integral like we've done before. Okay, but now we'd like to apply Stokes' theorem. Okay, so we're going to use Stokes' theorem and our answer to part A to compute the work integral around C2, where C2 is a different curve. It's the intersection of the cylinder x squared plus y squared equals a squared and the plane x plus z equals b. So let me just draw that for a second. So what we're going to have is in the XYZ coordinate system, okay, we're going to have our curve that we had before. Okay, and then that's our cylinder. So let me make that a nice base to the cylinder. Okay, and it's going to go up, and it's going to intersect with the plane x plus z equals b. And so that intersection is going to make an ellipse. It's going to look something like this. Okay? And so now we have C1 is here. And then what I'm going to do is I'm going to, in order to have my normal vector, say pointing outward like this, I'm going to need to orient my other opening to this surface in the other direction. Okay, so the surface you're going to think about is kind of the label of this cylinder, the label of my aluminum can. Okay, so I'm going to orient the curve in the other direction. Okay, and I'm actually going to call that negative C2 because it's oriented in the other direction. Okay. Well, what does Stokes' theorem say? Well, Stokes' theorem says, okay, that the sum of these two work integrals, if my surface is like the label of that can, well, the sum according to Stokes' theorem should be 0 because we established that the curl of B is 0. And this comes from Stokes' theorem. We would be doing the double integral of 0. Which, of course, is 0. Well, what that says is that the integral around C1 of B dot dr is in fact equal to negative the integral around negative C2 of B dot dr. So if we orient the curve in the other direction, if we do the integral around C2 so that it's now counterclockwise, then the integral around C1 of B dot dr is actually going to equal the integral around C2 of B dot dr. Okay. Well, that tells me that the integral around C2 of B dot dr is also 2 pi Ci, the same as the integral around C1. And so that's kind of cool. We had this integral around the ellipse, okay, which was difficult possibly to compute, but by Stokes' theorem, we can see that it's the same as the integral around, say, the base of that cylinder, okay? And it's cool because then you can say things like, oh, well, if you know the integral around the base here, right? Then I could actually expand this, make it a larger loop, and the integral around C2, okay, would be the same. And that's all due to Stokes' theorem.